Okay, today we are going to problem 2, 3, 4, and 28 of chapter 7. And for problem 2, a plane wave is incident on a layered interface as shown in the figure here. The indices of refraction of the three non-permeable median are N1, N2, and N3. The thickness of the intermediate layer is D. This one is D. And each of the other median is semi-infinite. Part A, calculate the transmission and the reflection coefficients, ratios of transmitted and reflected pointing flux to the incident flux, and sketch the behavior as a function of frequency. For N1 equals to N1, N2, N3 equals to 1, 2, 3, 3, 2, 1, and 2, 4, 1. And we can write down all the E field and B fields for incident, reflection, and transferred in positive wave and negative direction in N2 median, and the transmitted wave in N3 median. We can write down all the E field and B field in this way. And next, for non-permeable median, here our mu1, mu2, mu3 all equals to mu0. Vacuum mu here, and E field and B field parallel has to be continuous at each interface. This is our boundary condition. And here we can set in our ratio mu1 divided by mu2 equals to alpha equals to N1 divided by N2, and mu2 divided by mu3 equals to beta equals to N3 divided by N2. And for z equals to 0, we have the boundary condition for E parallel and B parallel between the incident wave, reflective wave, and the positive direction, negative direction wave. Here we can write down these two equations, and B equations can change into this one. And sorted, we can write down the incident wave. Incident E field can be write down in corresponding to the positive direction wave and negative direction wave, and reflection E field can write down in this way. And for Z equals to D, we have another two equations similarly, and the same we can sorting our positive wave and negative wave in this way. And next, we imply these two. We imply negative positive direction wave into here, and a negative direction wave into here, and we can expand our incident E field here in this way, and take out these two terms outside here, and sorting our coefficient, we can change our exponential minus ik2d and exponential ik2d into cosine and the sine term. Okay, and therefore we can write down our transmitted E field divided by incident E field equals to this one. And next, we calculate our transmitted coefficient. It will be equal to this one. So this term we have calculate in this page, and here we just need to calculate the value here. So we square, and in the square, this term will cancel each other. So this term will go to 1 here. and next we just sorting our coefficient, and finally we will get this answer. And for 1, 2, 3 equals to this one, and for 3 to 1 will equals to 1, 2, 3, and for 2, 4, 1 will be like this one. Okay, so this is for part A. For part B, the median N1 is part of an optical system. Median N3 is air. It is desired to put an optical coating N2 on the surface so that there is no reflected wave for a frequency omega 0. What signals A and index of refraction N2 are necessary? So we just calculate the refraction coefficient here, and just sorting our equation, we'll get this one. This one, we think about that. This one is positive. This one is positive because our N1 and N2 are all larger than 1. So these terms are all positive. So this has to be 0 here for the minimum, because we have no reflective wave. This equation has to be 0. So this one has to be negative. So N2 square substrate N1 square has to be negative. And besides, this is our N2 condition, and for thickness A, it just has to be satisfy this equation. This equation is our condition for thickness A. Okay, so we have many we have many answers for each N1. We have a corresponding A here. The answer is infinity. For problem 3, two plane infinite slabs of the same uniform isotropic non-permeable lossless dielectric with index of reflection N are parallel and separated by an air gap of width D. A plane electromagnetic wave of frequency omega is incident on a gap from one of the slabs with angle of incidence I. For linear polarization both parallel to and perpendicular to the plane of incidence, part A, calculate the ratio of powers transmitted into the second slab to the incident power and the ratio of reflected to incident power. So our wave goes like this in just showing us the figure here, and it is the same with the it's the same with the problem 2 in problem 2. Okay, it just different. It just has a difference here because our wave has a angle incident on the interface. So we can do some change on our alpha coefficient here. Okay, our alpha coefficient here, and corresponding beta will be like this, will equals to 1 divided by alpha. And here we have considered the n1 equals to 1, and n2 is n. Now n3 equals to 1 here. For the alpha and beta, we have considered the n here and here and here. Oh no, here is n and here is 1. Okay, n1 is n, n2 is 1, and n3 is n for our alpha and beta. And we can recall the answer from problem 2. We have this one, and we just use our new alpha and beta here. Our new alpha considering the angle coefficient, angle contribution, angle contribution, and we can easily calculate out the answer here. Okay, this is our transmitted power, and this is our reflected power. Okay, for part B, if incident angle is greater than the critical angle for total internal reflection, sketch the ratio of the transmitted power to incident power as a function of d measured in units of wavelength in the gap. Okay, so if our angle is larger than critical angle, that means our I larger than this one, and our cosine reflection will be equals to this one, and this is imaginary. So our alpha and our alpha, beta, and our phase will change into imaginary number. So we define the new alpha here, okay, and new phi here to our convenient. Okay, so our new alpha is here and equals to I alpha prime, and our new phi is here and equals to I phi prime. So we use the same formula, and we just change our phi into I phi. We just change our alpha into I alpha prime, change our phi into I phi prime, and just sorting our answer, and we'll get the answer here. And the reflected power will be equals to this one. And this is for part B. And for problem 4, a plane polarized electromagnetic wave of frequency omega in free space is incident normally on a flat surface of a non-permeable median of conductivity sigma and dielectric constant epsilon here. And for part A, calculate the amplitude and phase of the reflected wave relative to the incident wave for arbitrary sigma and epsilon. Okay, for non-permeable here, our mu prime equals to mu0, and it's the wave and the transmitted wave and the reflected wave. We have the notation here. For conducting material, alpha corresponding to epsilon, corresponding to our frequency, equals to this one. It's corresponding to our sigma here, conductivity here. So the wave vector will be equals to, can be write down in this one. So use the boundary condition. You can calculate out our reflective E field equals to K substrate K prime divided by K added K prime times incident wave, and this is our R here. This is our R here. No. This is our reflected E field divided by incident E field, and we define this one equals to Z, and it is a complex number here. And to calculate the amplitude, we do the calculation here, and just here we skip some steps to sorting our answer. We just I just directly show the show our answer in final steps. Okay. Then here we skip many simple sorting steps. Okay, and in the angle is equals to this one, and for angle equals to this one, and if this term is negative, that means we have the reflection here. So we have a pi. It will give a pi outside the tangent minus 1 here, and here will be change into we'll add a negative number here. Okay, so our angle has two answers here for different cases. Okay, so next, discuss the limiting cases of a very poor and a very good conductor, and show that for a good conductor, the reflection coefficient ratio of reflected to incident intensity is approximately R equals to this one, where delta is the skin depth. So for a very poor conductor, that means our conductivity much smaller than this epsilon 0 times sigma, or you can use sigma equals to approaching 0. So this one will be 0, and this one 0, this one 0, and this one 0 will have the answer here. And for our angle here, we will use some relation here below, and we will get answer 0 and pi for different cases. Okay, and this is for poor conductor. And for good conductor, the sigma is much larger than epsilon 0 times omega, and the skin depth will be equal to this one, and we sorting to this form. And the same, we just, so this term will much larger than this term, so this term will cancel. And this term, after some calculation, it will be equals to this one. It will be equals to this one, and we just do some sorting steps. After some sorting steps, we will get the answer will be like this, and R equals to this one squared. And after the squaring, and we negative the delta square term, the skin depth square term, the answer will be like this. Okay, so this is for part B. And for 28, A circularly polarized plane wave moving in the z direction has a finite extent in the x and the y directions, assuming that the amplitude modulation is slowly varying. The wave is many wavelengths broad. Show that the electric and magnetic fields are given approximately by the formation for E field and B field here. And here, where E1 head, E2 head, and E3 head are unit vectors in the x, y, z directions. Okay, since the wave has a finite extent in the two dimensions, the wave is now a plane wave. And assuming the wave is dominated by the transverse polarization, but have a small longitudinal part, the wave can be written as E equals to this one. We have the formula like this, and satisfy the Maxwell equation. The divergent E equals to 0 because there is no source here, and so we can write down our function corresponding x and y equals to this one, and we imply back into our origin formula, and we will get the answer here. Get the answer for E field here. And next one, the magnetic field equals to, we just use this use the boundary condition here, and B field will be like this. And since the amplitude modulation is slowly varying, these two terms are generally small. So, and we can neglecting the terms for the square term here. So these three parts will be negative. So this one, after curving, will all be negative, or will all be neglected. So we just calculate the first term, and we can write down, and we can write down the B field here, and with sorting we will get the answer here. So problem 22 is now done. It's okay. Okay, so just and we are all finished. So we can see you next time.